Well, good afternoon, everybody. We're back to live streaming. Hey, Chase, how's it going? I see your question, your hello up there. So, I figured we would maybe talk a little bit about the review problems that I posted for the lecture notes that were from yesterday to sort of start out. And then there was a question that Christina brought up on the discussion boards that she would like to see a review of some of the style of questions from the lectures that we had or the chapters we had before spring break. So let's go ahead and first talk about my review problems, then we'll get to other questions that folks have and Christina's questions as well. So let's start out with those example problems that I gave from yesterday. I did look at the homework and graded the homework. So all the homework that was turned in from last week has been collected and graded, and for the most part they looked okay. But if folks have questions on how those worked out, that was, I wouldn't say there were general problems, but there might have been some individuals that had a little bit of challenge with those. So let's go ahead and start with the review problems. If folks have questions, please don't hesitate. Just as they come to you, go ahead and post them in the chat, and I'll get to them as we go through. So I'll start then with review problems that I had posted as lecture notes as yesterday, and we'll go ahead and dive in on those. So the first one, it says, is that there were two charges. One that was positive, 1 microcoulomb worth, and the other one that is negative 2 microcoulombs. They're separated by 20 centimeters. So I'll draw the situation here. So this is charge, this is, say, charge number 1, this is charge number 2, and then the separation of those two charges, I'll just put a little dotted line there that I make it dotted. That's 20 centimeters. Alright, there we go, 20 centimeters. And let's say that this is the charge, this is the positive one. So it's plus 1.0 microcoulombs. And then the other one was the negative 2.0 microcoulombs. And the question was then, and make sure there's a decimal here. So there we go. Make sure that decibel's seen. And then the first question was, what's the electric field at a point midway between these two? So if I have this spot right here, what's the electric field there? And then later on, we're going to want to know what the voltage is there. So what's the electric field there? And then the second part of the question is, what's the voltage at that particular spot? So that's what we're looking at there. And we'll start with the electric field. So these are 2-point charges. So the way to go about this is we're gonna calculate what the electric field is due to each individual charge, and then add the two electric fields vector-wise, because each one is going to produce its own vector electric field. So this one, no problem. We just say the electric field due to that first charge. So I'll make it a little bit bigger here. The electric field due to this first charge, the one on the left, is KQ over R. K, remember, is 9 times 10 to the 9th. And the units for that are Newton meters squared per square coulomb. Okay, so there's K. I'm going to say this is the electric field due to the first charge, the one on the left. So I'll put the electric field that is due to the charge on the left. And then the charge that's on the left is the 1 microcoulomb charge. That's 1 times 10 to the minus 6. And there's coulombs. That's what a microcoulomb is. And then how far is this charge away from the spot where I want to know the field? Well, that's 10 centimeters, right? So I'm going to put in 0.10 meters. And remember, for the electric field, that's going to be squared. It's not a very good M, but imagine it's better than it is. And then the direction of this is where we put in the direction by hand. In this case, let's say this is along the positive. This is lying along the x-axis, and we can see here that the electric field point is to the right of a positive charge. Electric fields always point away from positive charges and toward negative charges. So the electric field due to this charge on the left is in the positive I-hat direction. So we can calculate what that electric field would be. I have a calculator right here. and it tells me 9 times 10 to the ninth times 1 times 10 to the minus 6 divided by 0.1 squared gives me a magnitude of 900,000, so that's 9 times 10 to the fifth. And that'll be newtons per coulomb, and it'll be in the positive I-hat direction. Now the electric field due to the charge on the right, we would just calculate that separately. Not my best E, but you get the picture. It's going to be the same sort of expression here, except I'm going to put the magnitude of the charge, now again, 2 microcoulombs. Remember, that's what we do with electric fields, just to remind you of that. We take the magnitude of the charge and forget about the sign for a minute to find the magnitude of the electric field, and then we put in the direction by hand. So this would again be 9 times 10 to the ninth. Instead of 1 times 10 to the minus 6, I would have 2 times 10 to the minus 6. And then it's the same distance away, so it'd still be 0.1 squared there. So let's plug in that number to get the magnitude. So 9 times 10 to the ninth times 2 times 10 to the minus 6 divided by 0.1 squared. And I get now twice as much electric field. That's 1.8 times 10 to the sixth newtons per coulomb for our magnitude. And now let's put in our direction here. So this is a negative charge. We only use the positive charge to calculate the magnitude of the electric field, but now that we have to find out what the strength of the electric field, or the direction of the electric field is, we have to figure out that sign. So remember, electric fields always point towards negative charges. So at this spot right here, towards the negative charge, is again in the positive I-hat direction. So the direction will be in the positive, I'll put the plus explicitly there, I-hat direction. And then the total electric field then at that spot would just be the sum of these two, and they're both pointing in the positive I direction. So when I add these together, I get 2.7 times 10 to the sixth newtons per coulomb in the I-hat direction. And I'll put a plus sign there just for flair. Okay, so that's the electric field. Oops, wrong thing. There we go, we'll go there. Okay. So I'm not seeing any questions so far, so hopefully this is relatively elementary. Folks are sort of remembering how we do this for individual point charges. I'll just keep going through this right now. I'm going to erase the electric field part of it. Hopefully that wasn't too complicated. Folks are sort of used to that. And what I'll do now is erase this and that. And we will then refer to the second half of the question, which asks you what the voltage is. Now the voltage, when we can find the voltage due to a point charge, I'll write down the expression for that just to remind us. That was from last week. The voltage due to a point charge is K times Q over R. Now, when we're calculating the voltage, though, we do use the sign of the charge. This doesn't have a direction for it, so we don't have to worry about putting the direction is because the I see Chase had a question here, but let me finish my thought here, and then we'll get to that. So the voltage is just a scalar, so the sign of the charge, we are going to put it in here. And then remember, the difference here is it's just R, not R squared down there. So Chase asks or states, I'm not sure which it was, EL is 10 to the fifth. Yes, I think it was. I calculated it as 9 times 10 to the fifth. That's what I got for my number. So, and then the other one was times 10 to the sixth. So when you add something times 10 to the sixth and 10 to the fifth, you just add those little things. So it's 1.8 plus 0.9 times 10 to the sixth. That's why I got 2.7 times 10 to the sixth. Okay, so hopefully that clarifies it if there was a clarification necessary. So the voltage here is simply going to be, take the voltage due to these individual charges, use the sign in the Q here, and then just add those together. So it would just be the total. I'm just going to put them all together on one line here rather than separate it out as separate things. So it'll be 9 times 10 to the ninth. This is a common factor. Newton meters squared per coulomb squared. That goes there. That's going to be a common factor between each of the two charges. The charges and the distances could be different, but I'm just going to factor the k out. So kind of what I'm doing here is k times q1 over r1 plus k times q2 over r2 here. Just kind of separating them out. But notice that k is a common factor. I can pull out there so I don't have to multiply twice times 9 times 10 to the 9. So I'm going to do q1 over r then. So q1 is, again, r1 times 10 to the 6th. Minus 6, sorry. Coulombs. The distance now, r, is, again, 10 centimeters. So that's 0.10 meters. Okay, so this is the contribution due to this charge. The second charge, I'm going to add the voltage there. There's a negative charge there, so that's going to be important. 2 times 10 to the, I'm going to run out of space, but imagine you can see this. Maybe, there we go, we can kind of do it. Okay, and then again, it's the same distance away in this case because it's at the point which is halfway between the two. So I'm going to put my bracket there. All right, there we go. So then what would the voltage be due to these 2-point charges? So I'm going to do, this is going to be negative. We see 1 over 0.1, or 1 times 10 to the minus 6 over 0.1 plus negative 2 times 1 to the times 10 to the minus 6 over 0.1. So they're going to partially cancel, but the larger charge is going to win here. And then times 9 times 10 to the 9th. Let's see. Oops. Times. All right. So I get negative 9.0 times 10 to the 4th. So that'd be negative 90,000. And then if you look at this, the coulombs, one of them cancels out, and one of the meters cancels out. Newton meters is what's left in the numerator, which is a joule. And then coulomb is what's left in the denominator, so that'd be a joule per coulomb, which is the same thing as a volt. There we go. So it'd be 90,000 joules per coulomb, or negative 90,000 joules per coulomb, or negative 90,000 volts would be the potential at that spot. Okay, so that's the first one. I'll pause here for about 10-15 seconds and see if there are any questions on that one. And if you say no questions, the other thing is you could say hurry up and get that other example problem or something like that. So feel free to tell me which of the example problems from the lecture notes you would like to see, and then I'll start taking other questions as we work through whatever ones are there, and also look at Christina's questions for the live stream that she asked on the discussion board. So Sammy asks, how come E sub r was positive I hat rather than negative I hat? The reason for that was, luckily we still have our picture up here, the reason for that was at the spot where I want to know the field right here, this is a negative charge. Remember that electric fields point towards negative charges. So the electric field due to this negative charge at any point in space is going to point towards that negative charge. Notice that at this spot right here, towards the negative charge is to the right, which is the positive I hat direction. Okay, hopefully that clarifies. And I'll pause for any other questions too. No problem, Sammy. Okay, so I guess I'll look quick at the second example problem here. Let's see what we got here. Oh yeah, this was the one that was kind of similar to one of the homework problems. Hopefully it's not too bad, but we'll have a look at it here. I'll check the chat here. Okay, all right, looks good. All right, so I'm going to erase this one for now. I guess we'll try to clear that up. And then this one says, and like I said, this is kind of similar to one of the homework problems. So if that one looked complicated to you, then this one hopefully will give you a little bit of clarification on that. It seemed like it went okay to me, but we'll see how it goes. So let's say we've got this line of charge that has a length. It sits at x. One of the ends sits at x equals 0 like that, right up there at the origin on the x-axis. So let's say that's the positive x-axis, like that. And then the length of this thing is L. And then the charge density of it there is given. Okay? And then we want to know what the electric field is at x is equal to negative L. So I guess that'd be over here somewhere. Let's not make it an X marks the spot, because that could get mixed up with what our X is there. So I'll just say there's our point. Let's see, let's do this. So there's our point. I'll make it just bigger. There we go. All right, and then this distance from the end of the rod to there is L. That's at position x is equal to negative L. We want to know what the electric field is at that point. So what is it right there? Knowing also that the charge per unit length, the lambda, is now a function. I wrote it down as it's equal to some constant alpha times x plus L, which is a little bit of a weird expression, but I just did it because I'm showing you kind of what you might see when exam time rolls around. Okay, so let's use the formulas that we, sort of the procedure that we know about, just to remind us how we calculate the electric field. So what we're going to imagine doing is we're going to chop up this distribution here into tiny little itsy bitsy pieces, each of which has a particular position for our coordinate axis, and we're going to ask ourselves, all right, how much charge is in that little bit of the distribution, and then also, what is the vector which points from that piece of the charge distribution to the field point? Find its magnitude, find r hat, and the unit vector that points from the source to the field point, and then go from there. So this one is relatively pedestrian, relatively simple, but we're going to go through all the steps just so that we're all sort of on the same page, because this is from something before spring break. All right, so what we'll do, let's see. I just got an error that you're not receiving enough video or something like that. So let me check something. I think it's okay. Hopefully you're not receiving too much buffering. So sorry if it's going to buffer a little bit, but you'll have a chance to look at it later as well. If there's sort of trouble. So here's what we're doing. We're going to break this down, and the position of this arbitrary little spot on there is position x. The length in there, the length of that little piece is dx, because it goes from the left end of x all the way up to x plus dx. Okay, so there's our position. So now let's write down how much charge is in there. Okay, thanks, Chase. That's good to hear that that the buffering isn't too terrible. Sorry about if it's a little bit laggy. My internet is being used by more than one person for a live chat or live video right now. So my wife is working from home as well. So hopefully latency isn't too bad. All right, so let's look at the charge inside of that little piece. So there's a little dq that ends up inside that little bit of space there. That's going to be equal to lambda, the charge per unit length, times the length of that little bit, which is dx. And of course, lambda is equal to this thing which depends on x. So it'll be alpha times x plus L, that whole expression times dx. x. Okay, so then what I want to do, the next little bit is, well, what is our vector? Okay, what our vector is the vector which points from our arbitrarily little chosen spot here back to the field point. Okay, so notice what is the the vector that points from here to here? That's what we're going to call our vector. Well, I look at that and I say to myself, well, that to me looks like it's the vector has a magnitude, whatever x is, plus this extra length. So a vector, so if I'm at x equals 0, it would be just that, just be L. But if it was, further over, position x, it'd be x plus L. So it looks like it's x plus L. And to me, that looks like it points in the negative I hat direction. Now, like I said, this is a little bit of overkill. It's not terrible to do this one, but going through the steps is usually useful. So since this is all in one dimension, the magnitude of R is just x plus L. And then R hat, which is R vector over R, is just negative I hat. I'll put it in parentheses just to, for flair. Okay, so we've got all our pieces now that we can use to build this integral. So I'm going to move this down a little bit. We don't have a ton of space. Maybe I'll try to make some more space here, just in case we need it. Okay, so now the electric field at that spot will be equal to KQ over R, the integral of, I'll just put it, just generally K times dq over R hat, and then I've got to integrate over the whole thing. Okay, so in this case, K is going to be a constant. It can come out of the integral, so I'm going to pull it out of the integral. Okay, and I'm going to make my integral sign nice and big here. Okay, and then my dq, I plug in what I have here, what I wrote down, that was alpha times x plus L, and then times dx, so that's dq. Whole thing is dq. Now divide by the magnitude of R, which we just had here. So there's our piece that we're going to put there. So that's x plus L. Remember that it's the magnitude of R squared. So it's x plus L squared. And then R hat is negative I hat. So I'll just put that in here. Negative I hat. All right. So now I've built this. I built the lambda so that it would have a nice little, so it would do some canceling here for us. And that's typical of what you might see on an exam as well, where I make it so that the integral is easy to do. So the setup is important and valuable and useful, but I'm going to construct it so that the integration is actually simple. Now what I need to do here is I have to go, well, what are the values of x that correspond to all the little pieces here? Well, it starts out at x equals 0 and goes all the way out to x is equal to L. So that's my limits of integration. I'm going from x is equal to 0 to x is equal to L. Notice that this is going to cancel partially with that, so that this integral gets a little easier. I'm going to stretch this out a little bit more so I have a little bit more space. Okay, so now this integral becomes the integral of, I'm going to have negative k times I hat. That's the k, and I bring the I hat out from the integral. And then oh yeah, and I suppose I should have an alpha out there too, so I'll bring the alpha, that's a constant as well. And then it's just the integral from 0 to L of dx over x plus L. Okay. Now, what you can do to solve this one is you can do it via substitution if you like. The way that I would do it is I would say, I'll show you the little substitution here. I would do the z substitution. I say z is equal to x plus L, which implies that dx is equal to dz. So I can do that substitution for dx there. I can turn it into ze, dz. And then wherever I see an x plus L, I can replace it by z. So this integral becomes negative k, I'm going to rearrange these a little bit, times alpha times I hat, the minus sign indicating the direction there. And then I'm changing this integral over to the integral of dz over z. And of course, when I switch over to the new variable z, I have to change the limits of integration because these are the limits on x. What are the limits on z? Well, I'm going to switch my limits. I'm going to say, well, x equals 0, what's z? In other words, what does this lower limit correspond to? Well, when x is equal to 0, z is equal to L. So it's actually the lower limit in z becomes L. And then the lower limit, or sorry, the upper limit when x is equal to L, well, when x is equal to L, z is equal to 2L. So there we go. All right, I'm going to erase this little space down there so we can finish this out. Okay, now when I perform this integral, this is just a natural log, right? The integral of dz over z is the natural log. I get negative k times alpha times I hat. And then I get the natural log of 2L. I'm going to put a bracket there, minus the natural log of L. And remember that the difference between two logs is the logarithm of the ratio of the two arguments. So this, when I take this difference, that's the, if we do our natural, some of our things with natural logs, this is the natural log of 2L over L. The natural log of 2L, the quantity of the of 2L over L, which you can cancel out the L's. So this ends up being negative k alpha I hat, and then it's the natural log of 2. And there's my answer. That's it. Done and done. Okay, does that make sense? And some of that is just, it's not really window dressing. It comes out to a nice form there with the natural log of 2 and k and alpha and stuff like that, but you could have left it in this form as well and it's still correct. There's no mistake there, but I like to simplify it as I can. Because the reason I like to simplify natural logs like this when I evaluate it is because normally you want to take the logarithm of a number, not a number with dimensions. So the this length here could be like 3 meters or something like that, or 1 meter, 7 meters. It's a particular length. It doesn't make a lot of sense to take the logarithm of 3 meters because what units would it have? What's the logarithm of a meter? That's kind of a weird concept. So, but since you're evaluating it at these, at 2L and L, and you take the difference, that becoming the ratio of the two, then the L cancels out, and so would the units along with it. So it's actually really sort of physically desirable, not just mathematically desirable, physically desirable because of the problem with the units, that you should take the logarithm of the ratio of the two things that you're taking that you're evaluating at the endpoints, and that gets rid of the units because the units would cancel, and then you get the natural log of some number, which is nice. Okay, so I'm going to pause here and see if there are any questions. If you want to see what's sort of the next question that you want to see. Because I can do the third example problem, but I really want you to drive the questions here if you have it. So first of all, is that clear, I guess? And then do you have further questions that you would like to analyze and look at? Okay, Chase is asking, after the third example problem, can I go over an example problem about conductive surfaces? Okay, so I'll clarify. I'll clarify with you what you mean by a conductive surface in a second, but I expect you mean when we have conductors and then we place charges on it, how does it distribute and that sort of stuff. Okay, so Cole and Sabby say it's clear and it looks good. Okay, so I guess I'll go over to the third example problem. And remember, I am remembering that Christina's questions I've got to look at yet too. Those are good ones to think about. Okay, so let's clear my space here so we have a little room to work. Okay, so the third example problem was kind of daisy chaining back to the question that we talked about earlier. The question, so I'll sort of redraw that. I guess I should have kept it, but so the situation is we had our positive 1 microcoulomb charge, and then over here we had our negative 2 microcoulomb charge, and separated by 20 centimeters. And then we're saying that there's another charge that starts out at this spot right here. And this charge, the moving charge, is going to go from here to some other spot. Okay? So it's going to move from here to a spot that's 5 centimeters from the positive charge over here. So it moves from 10 centimeters away to 5 centimeters away. Okay, so it's moving from there to there along this line. Okay, so the question then is if the charge that's moving, so I'm going to call that little q. The charge is a positive 2 microcoulomb charge. And it starts there and it goes to there. Okay. And the question then is, what is the change in this third charge's electrical potential energy during that move? Okay, so this is what we're going to do. The way to sort of look at this one is we calculated the voltage at that particular spot. That was one of the things we did in the first problem. I don't remember what it was off the top of my head. Was it negative 90,000 volts, I think? Let me check. Maybe the folks are... Okay. Okay. Let me do a quick check on that one. Let's see. I had one. Oops. Exponents. -6 divided by 0.1 times 10 to the 9th. All right. So the voltage at this spot right there, I'm going to call that, let's call this point A, and this spot here where it's going to finish, we're going to call point B. The voltage at point A we had as negative 90,000 volts. Okay, so that's what we had. So now we're going to calculate what the voltage is at point B, where it finishes. And the reason I'm going to do that is that, and I'll write down the general expression over here, the change in the potential energy in going from point A to point B is equal to the charge, which does the moving, times the change in voltage between point A and point B. So we're calculating the difference in the voltage here. It starts out at negative 90,000 volts, and as it moves to point B, that voltage is going to change. Okay? And we're going to find out, well, by how much. If I multiply the charge, then that isn't going to be equal to the change in the electrical potential energy in having that 2 microcoulomb charge move from point A to point B. Okay? So let's calculate what the voltage is at point A. Or sorry, at point B. My mistake. Okay. All right. So we're going to calculate what the voltage is at point B. Again, we're going to use that same sort of expression. We have a couple of point charges there. So it's going to be 9 times 10 to the 9th Newton meters squared per Coulomb squared. And then we're going to do that, Q over R for each of the two charges. So the first charge, the one on the left, is 1 times 10 to the minus 6 coulombs. And now we have to divide again by how far away point B is from that charge. Well, now it says in the problem it's 5 centimeters away from the positive charge. So it's pretty close. So 0.05 meters away. All right, so there's that one. All right, so that's the voltage due to that one. And then what's the contribution to the second charge? Well, the second charge is negative 2 microcoulombs, negative 2 times 10 to the minus 6 coulombs, divided by, now how far is this one away from point B? Well, that's 15 centimeters away. 0.15 meters. So they're different distances away, and this is going to mean that the voltage at B is going to be different than this one. So let's see what it is. We've got 1 times 10 to the minus 6 divided by 0.05 plus negative 2 times 10 to the minus 6 divided by 0.15, and then take that result and multiply it times 9 times 10 to the 9th, and I get a positive voltage of 60,000 volts. Okay, all right. So now, if I want to see what the change in the electrical potential, or let's first of all calculate what the difference in voltage is then between those two. Okay, so difference in voltage is always going to the final position minus the initial position. So we finish at point B, starting at point A. So that is 60,000 minus negative 90,000. So this is an increase in voltage. 150,000 volts. Okay, so we've gone from negative 90 to positive 60,000 volts in going from point A to point B. Now the change in the electrical potential energy is Q times delta V as usual. Which Q are we talking about? It's the charge that is moving from point A to point B. And it was a positive charge. It was a positive 2.0 microcoulomb charge. So I'm going to say, well, this is positive 2 times 10 to the minus 6 coulombs times the change in voltage was positive 150,000 volts. Okay, plugging that into my handy dandy calculator here. That's 2 times 10 to the minus 6 times 150,000, and I get 0.30. All right, and the units of this, it's a coulomb times a volt. Remember, a volt is a joule per coulomb. So in that case, the coulombs would cancel out. This is actually then an increase in the electrical potential energy of 0.30 joules. Okay. So I'm going to look and say I didn't have to. Yep. Okay, we're still good. No other questions that have arisen so far, so that's okay. All right, so the next question is, what sort of work is done in moving this charge? Positive work or negative work? Okay, so this is a way to think about it, and this sort of harks back to what we talked about in Physics 1081. So let's sort of review what we mean by this. Now, if you were to take a book or something like that and lift it, okay, so if I take this calculator, for instance, and I lift it upwards, the work done by you in lifting it is positive. The work done by gravity is negative because the gravitational force is down and the displacement's upward. So the same sort of thing is happening here. The work done by the electrical force, the work done by the electrical force in this case is equal to minus the change in the electrical potential energy that happens because of the motion. So the work done by electricity here, the work done by electricity is actually negative 0.30 joules. Now, that means in order to make this positive charge move from here to here, some external particle probably did work to push that. If it did it at constant speed, the work done by that force would have been 0.30 joules. I would have had to do positive 0.30 joules to make that happen. Then that would have caused there to be an increase in the electrical potential energy because of the negative work done by the electric force. Okay, does that make sense? I'm gonna check the stream here and see if that's something that folks understand. Is it good? Hopefully it's good. Okay, so Sammy says looks good. So what I'm going to do, I don't see any questions, but I'm going to get ready to erase. Clear. Okay, focus range is clear. Okay, good. All right, so I'm going to clear out my workspace here. All right. All right. So I think Chase, maybe your question about conductive surfaces and stuff like that, some of that might be dealt with by by some of the questions that Christina asked. So I'm going to get into. I know that there's probably some other questions out there, but Christina asked some specific ones, so I will address those next. And then if other folks have questions, feel free to ask them in the chat. I will get to everything that's in the chat eventually. So so let's start with the questions for live stream. Christina specifically asked, could you go over a couple questions from earlier chapters from before spring break? Questions I would like to review are 2217, 2221, 23.3, and 23.11. So the chapter 22 and chapter 23, some example problems like that. So let's see. I will have a look at 2217 to start with. And 2217, for those that don't have their books, to follow along with necessarily easily here, it's that we have two charges on a. This is not going to be simple to draw for me. It's a trapezoid. They're on sort of opposite corners of a trapezoid. Where the angle that each side of the trapezoid makes with the horizontal that's a 45-degree angle there. So I'll put 45 degrees for both of them. And then we'll use the geometry thing. There we go. There we are. So this one is, this charge up here is plus Q, it says. And then this one also down here in this opposite corner here is positive Q. So they're both the same amount of charge. Okay, and then the question for number 17 is find symbolic expressions for the total electric field at the point P, which point P is here. So that's point P. And then this point opposite it right there, this is point P prime. It asks for the electric field at both of those spots. And I'm going to say that I think in a sense, it would be a little bit repetitive to do both point A and point B, and I want to make sure and get to as many questions as possible. So the way to look at this then is, let's calculate it just for part A, just for point P, and then from there, hopefully it would be pretty straightforward how we would go about P prime, because you do basically the same process, just slightly different look. So just to finish out the picture here, the length between Q and this charge here and P is D, and the length of the bottom is 2D. So the distance from here to here is twice the distance along the top. Okay. So what is the electric field at point P due to these two charges together? And it's not too terrible here. If we look, what's the electric field at point P? It's going to be the electric field due to these two individual charges. I'm going to put it at point P. And I'm going to actually just combine the two here so that we can kind of do it sort of in one fell swoop rather than separate and then add them. Okay, so the way to look at this then is, let's look at this charge right here and its electric field that it produces at point P. So that would be equal to K times the magnitude of that charge, which they're both positive, so we could just don't have to worry too much about that. So we got Q, and then over. Now, how far is this charge here from point P? Well, to me, it looks like it's it's D away. So we're going to put D squared, because remember it's KQ over R squared for the electric field. And then in this case, that would be equal to, it would produce an electric field, which it's a positive charge, so it points directly away from that. So that's going to be in the positive I hat direction. Okay, so that is the electric field due to this charge here at point P. Now, the challenge, of course, is recognizing what the electric field is due to this charge down here is at that spot. And we have to figure out what this length is right here. All right, so there's a little bit of geometry involved, and then I'm going to do the geometry. Since it's symmetric here, I'll do the geometry over here so it doesn't get too busy where I've got my 45 here. Okay. So I need to figure out what this length is, with this being a 45-degree angle, and I kind of have to figure out what this distance is right here. Okay, knowing that the distance from here all the way over here is 2D, okay, and I know that this distance, so I know the distance from there to this spot directly down. I know that this is D from here to here. So I know that this distance from here to here and from here to here, each of those needs to be D over 2, because the total length from P prime over to Q is 2D. I know this distance from here to here is D, so that means I got to add another D over 2 here and another D over 2 here. Adding that to the D in the middle gives me the 2D that I expect. So this distance right here across the bottom to the spot directly below it, I know that that is D over 2. Okay, so using that, I can figure out, since this is a 45-degree angle, I can figure out what this distance is, and that would be the same distance as it is over here. So I know then, using my algebra here, or my trigonometry there, I know that the cosine of 45 is equal to the adjacent leg over the hypotenuse. The hypotenuse is what I want to know. So that's D over 2. That's the adjacent leg over the hypotenuse, which is going to be, I'm just going to call it R for now. That's the distance between this charge here and that spot up there. Okay, so what's R? So first of all, the cosine of 45 is the square root of 2 over 2. That's equal to D over 2 all over R. So that means I could solve here for R. That to me looks like I multiply both sides by 2 and divide by the square root of 2. So that gets rid of the 2 there. It looks to me that's D over root 2. Something like that. Okay, so that's R. So now I've got the distance between charge, this charge here and P, which is what I want to know where the electric field is. So it's going to be plus. So it's this piece right here plus, I'm doing this kind of on two lines, K times, again, the charge is Q. And now I say, well, this is going to be R squared, which that's going to be, notice that that's in the denominator here, I'm going to have D squared over 2. When I square the square root, I get 2. So notice that 2 in the denominator there, from the square, we can just bring up. And oops, I'm going to erase that because that was going to turn into a D and it didn't go. All right, there we go. Okay, and then there's the D. And then what I need to do is take into account the fact that, so that's the magnitude. Oh, that's D squared, sorry. D squared. There we go. And then I have to take into account now, that's the magnitude. What is the direction that's associated with this? Well, this is a 45-degree angle there. So I know that the I hat and the j hat components are equal to one another. They're the cosine of 45 and the sine of 45 respectively. Each of those has an amount of square root of 2 over 2. The I hat component is minus root 2 over 2. And then the x, remember, points away from positive charges. That's to the left and up. So the upward component is square root of 2 over 2. And we're going to put that one as j hat. Okay. And that does it. So the common 2's that you have there, you could cancel if you wanted. And then we could add the I components if we like. But everything is K times Q over D squared now. So the electric field at point P would be, if I gather the two I hats together, I've got a magnitude of K, or a common factor of KQ. That's supposed to be a K. There it is. Over D squared. Now I've got 1 I hat minus root 2 I hat. Okay, so 1 minus root 2. So I'm going to put it as like this. 1 minus root 2. There's the I hat component. And then I've got the j hat component is root 2. J hat. And it's something like that. Okay. And really, it's at this point, once you've got past this spot right here, it's just massaging it to kind of sort of look nice. It's not critical. I mean, there's this answer, if you just take this and you add this piece to it, it's right. It's correct. There's no mistake. If you want to clean it up on an exam or something like that, you're welcome to do it. But you can, that's if you've got time, right? So just, if that's the result that you get and you're happy with it, it's right, you're sure there's no mistake, you can just leave it like I have here. With this part and this part added together. You don't have to necessarily combine the I hats unless you really feel like you want to make it easy for me to grade or something. Okay, so hopefully that one was clear. And again, this is point charges. We're just adding the electric field due to each individual point charge. And notice that this positive charge here, the electric field points directly away from it at the point where we want to know the field. This one, again, it's a positive charge, and pointing directly away from it here points 45 degrees above the next negative x direction. That's why we get leftward and upward with equal components because it's a 45-degree angle. So we're using the cosine of 45 and the sine of 45. Cosine of 45, root 2 over 2. Sine of 45, also root 2 over 2. Okay, so I'll pause and see if there are any questions on that one. P prime would be the same sort of thing, except the electric field due to this one would point directly to the left, and it's 2D away. This one would be the one that's pointing down, this one would point down and to the left. Two would add up, and rather than, we've calculated this distance already, but it's just a different value. Okay, is that clear? Okay. All right. If there are no questions on that, then I'll clear this one out so that we can give ourselves a little space to work some more. And Christina's second question for the live stream was on number 21 out of the same chapter, and that's where we've got, it's not too bad either, but we'll have a look at it. It says there are 3 charges arranged in a particular way. One of them's along the x-axis, one of them's on the y-axis, and one of them's basically at the origin. Okay, so let's say I've got a charge there. This one and that's underneath along the y-axis is -3 nanocoulombs. This charge here is a positive 6 nanocoulomb charge. Okay, nanocoulombs, 10 to the minus 9. Okay, and then the third charge is at the origin, and that one is 5 nanocoulombs, positive 5 nanocoulombs. I guess I'll try to put it here. And the distances involved here, I'll maybe make them in a different color so it doesn't get too busy here. But so this I'm going to use a slightly smaller brush so I can, or size. Hopefully it's still visible, but it's a little finer. So this one is 0.3 meters. So it's 30 centimeters along that axis, and then the vertical distance between the origin and the position of the -3 nanocoulomb charge is 0.1 meters or 10 centimeters. Okay. The question then asks, first of all, part A is find the vector electric field that the 6 nanocoulomb and the -3 nanocoulomb create together at the origin. And then part B is find the force vector on the 5 nanocoulomb charge. So the electric field at the position at the origin where this 5 nanocoulomb charge, positive here just to make it clear, 5 nanocoulomb charge exists. Okay. So not too bad here. Let's do it. Let's find the electric field at the origin. Again, it's a point charge style problem. There's the electric field due to this one, which notice that points directly away from it since it's a positive charge. So that one I'll just calculate. Hopefully we've seen this. It's kq over r squared. So it's 9 times 10 to the 9th times the charge is 6 times 10 to the minus 9. And then I'm going to divide by the square of 0.3. Okay, so that one is 4.86. That is the magnitude of that electric field. 4.86 newtons per coulomb. And now, so that's the magnitude of this one. Remember, we're using this formula in general for each individual charge. It's kq over r squared for the magnitude. And I'm going to put the vector there, and I'm going to put r hat there, so we've got it all down. Okay, so kq over r squared. So that's what I did here. I got 4.86 newtons per coulomb. Now, the direction, this is a positive charge. At this spot right here, what is for positive charge, remember the electric field always points directly away. Away from the positive charge at that spot is in the negative I hat direction. Okay, the magnitude, just using the 6 without the sign, gives me a magnitude of 4.86 newtons per coulomb. And then the direction is minus I hat. Now this one, okay, what's the magnitude of that one? Okay, I'm going to put plus here because we're going to have to add the electric fields, vector-wise. So I'm going to use the, again, 9 times 10 to the 9th times. Now the magnitude of the charge here is 3 nanocoulombs. So times 3 times 10 to the minus 9. Okay. I'm stripping off the sign because we're just worried about the magnitude. We'll put in the direction later, and that's where the sign comes in. And then how far that one is away is 0.1. So I do 0.1 squared in the denominator, and I get let's see. Oops. Let's see. 9 times 10 to the 9th. It doesn't seem right. Just a second. Well, maybe it is right. Okay. No, it doesn't seem right. Let me check. 9 times 10 to the 9th times 3 times 10 to the minus 9 is 27. Okay, that's right. Divided by 0.1 squared is 2700. All right, just let me check the other one though. 9 times 10 to the 9 times 6 times 10 to the minus 9 divided by 0.3 squared. I might have made a mistake. Yeah, all right, that's a mistake. Sorry, that's a mistake here. There's a mistake. This number is incorrect. You probably figured that out already. That number should be 600 rather than 4.86. I'm not sure what happened. There was a glitch when I entered in my calculator. Okay, so all right. So the second one. Sorry about the mistake there. It's live. So then the second one is 9 times 10 to the 9th times 3 times 10 to the minus 9 divided by 0.1 squared gives 2700. All right. So the magnitude of that one is 2700 newtons per coulomb. Okay, now let's put in the direction. That might change our plus here, but we're adding these vectors anyway. All right, so negative. A negative charge, the electric field points towards the negative charge. Now, at the spot we're calculating it is here, towards the negative charge is downward. So, in fact, I did have this, I have to add a negative j hat direction. So I'll put that in, negative j hat. And there we go. There's our electric field. Okay, there's our electric field. So now that gives us what the electric field is. That's what we wanted to know. That was for part A. For part B, it says find the vector force on the 5 nanocoulomb charge that is sitting at the spot where those two are producing the electric field. So for part B, to calculate the electric field, remember our original definition of the electric field. It is the electric field, or is the electric force per unit charge. So I can use that definition back that if I have a charge that is experiencing an electric field, the electric force on that would be equal to the charge of the recipient times the electric field that the recipient is experiencing. So in this case, we have a 5 nanocoulomb charge. It is a positive 5 nanocoulomb charge. Oops, that's supposed to be C. There we go. There it is. And I have to multiply it times this electric field. Which is a vector, so you're going to get a vector result. My mouse drawing skills leave something to be desired, but we still draw. Okay, so the x component would be 600 times 5 times 10 to the minus 9. It's going to be so it would be 3 microcoulombs with a minus sign in front of it, so 3.0 micronewtons, 10 to the minus 6 newtons. And then we would, for the second one, when we distribute that in, 5 times 10 to the minus 9 times 2700. And that one is, again, we get a minus 13.5 if we wanted to put it like that. Micronewtons in the j hat direction. Okay. So that would be the force on the charged particle, having I and j hat components. Okay, so I'll pause on that one and see if folks are clear about how that worked. Meanwhile, I'll sort of get ready for the next example that she was asking about. So any questions on that one? Is that one clear? All right, so we're getting a lot of practice on electric fields and forces and stuff like that, so I think that's good. And we're seeing how point charge is really the start of everything here. Let's see. Okay, cool. Looks like folks are clear on that one. Hopefully Christina found that one when she watches this one later. Hi, Christina. When she has a look at it later on, hopefully it's also clear to her. Okay, so the third question she asked about was 23.3, and that says we've got a uniformly charged ring of radius 10 centimeters, and it has a total charge of 75 microcoulombs on it. So this is a ring, not a disk, but a ring. Find the electric field on the axis of the ring at a bunch of distances. One is 1 centimeter away, one is 5 centimeters away, 30 centimeters away, and 100 centimeters from the ring. All right, so the situation is this. We've got this ring, okay, and it's a ring of charge. So I'm kind of drawing it in 3 dimensions here. So this is this ring of charge that has a particular radius r and a total charge on it q. And we want to know what the electric field is at various distances directly above the center, which I'm going to call z. Okay, and then this radius right here, the radius of the ring, is I'm going to call capital R. I believe we did a problem similar to this. I'm going to look and see if the book has an expression for this, because I think it might have worked this as an example problem where that's it. So let me see if it has that expression. It does. There's a problem in section 23.1 where we have a uniform ring of charge with a radius A, which we're going to call a capital R, I guess, and a total charge on it Q. Okay, and then it's saying the distance away above the axis is X, and we called it Z. So this is what we're going to do. We're going to use the electric field formula for that, and this is completely legal. Okay, first of all, the electric field, we're just going to do the magnitude. We're not going to worry too much about the direction. If it's a positive charge on it, it's going to be directly, along the z-axis as I've drawn here. But I'm going to adapt the expression that they have in the book, which is K times, I'm going to call it, they called it X. Remember, this, just so you know, this is on page 619. It's the same situation, except they turned it sideways. Okay, so it's along, this is along the x-axis and that sort of stuff. But so it's the electrostatic constant times x. Well, x is their distance away from the axis, so I'm going to call it z. And then they have an expression. They say a squared plus x squared to the 3/2 in the denominator. Well, their a is the radius, so I'm going to call it r instead of a. So there's r squared. And then they have plus x squared. Well, x for us, it's z squared to put in there. And then this is to the 3/2 power in the denominator. And then multiplied times capital Q, which is the charge on the ring. So this one becomes pretty, not too bad actually. It's pretty easy to solve because all we have to do now is plug in the various values of z for the radius and the charge that's on the ring. And remember what the electrostatic constant is. So it's just a matter then of putting these, plugging those values in. So part A, and so this R, I guess I'll put this here. R in this case happens to be, they say it's 10 centimeters, so it's 0.10 meters. The charge on the ring is 75 microcoulombs. 75 times 10 to the minus 6 coulombs. So A says, well, what's the electric field at that spot when the distance we're talking about is 1 centimeter? And then B is just what would it be if if Z was 5 centimeters. 0.05 meters, and so on and so forth. Okay, so let's do one of these, and then we'll see the other one. It's going to be basically a plug and chug exercise once we have this expression. Okay, so I'm going to ask now as I work through this. Okay, I'm going to ask the chat, would you like to see me perform the integral to calculate what the electric field is at a point Z for, directly above the center of a ring? If you want to see me do the integration for that, say so in the chat while I do this plug and chug exercise, and then I'll do it. So let me know what you want as I'm working this, and I'll check back once I'm done and see if you want to see further clarification. Okay, so let's calculate what the electric field is at 1 centimeter above the center of the ring. So this would be plugging in this values. We'd have E, the electric field as, I think we're going to need more space. So I'm going to give myself more space. I'm going to go underneath. Oops. All right, so underneath. We're going to say the electric field. More space. Electric field, the magnitude of it at least is going to be, so K is 9 times 10 to the 9th. That'll be Newton meters squared per Coulomb squared. So there's K. Okay, Z, in this case, Z is 0.01 meters. Q, 75 times 10 to the minus 6 coulombs. And then underneath it all, we have R squared plus Z squared to the 3/2 power. Oh, we got some more junk down here. Let me clean that up. Okay. So now we have R squared plus Z squared to the 3/2. So this would be, now make myself a nice big bracket, R squared. So the radius of it was 0.1 meters. Squared plus Z squared. In our case, Z was 0.01 meters. And then once we've got that, we're going to take that to the 3/2 power. Okay, so what would the electric field look like? I'm going to calculate the denominator first. 0.1 squared. 1 squared. Okay, I'm going to take the square root of that and then cube it. Okay, times 9 times 10 to the 9th times 0.01 times 75 times 10 to the minus 6. And what I get is 6.65 times 10 to the 6th. And if we go through this, I'm pretty sure we'll get newtons per coulomb. And that would point directly away from the center of this thing, straight up along the z-axis in this case. Okay, so now let me check here. Okay, all right, so Chase is asking for example problem that has charges placed inside and outside out of conductive solids and or conductive shields. Okay, all right, yep, I'll get to something like that. See you later, Chase. Okay, are there any other questions on this one, or do folks want to see the calculation of that integral? How to get this expression for the electric field? And I'll pause here to see if there were any further questions on that. Yep, you too, Chase. See ya. Okay. Well, I'm gonna then erase this out. It seems like there's not a lot of call to actually perform that integral for y'all. You've seen enough of them, I guess. I'm okay with that. All right, and then the last question that Christina had was number 11, which says we have a flat surface that has a particular area, 3.20 meters squared, is rotated in a uniform electric field that has a magnitude of 6.2 times 10 to the 5th newtons per coulomb. All right, the question then is to determine the electric flux through this area when the electric field is perpendicular to the surface and when the electric field is parallel to the surface. All right, so I'll draw this out so we can sort of see what the question is asking. It's saying, let's say we have an electric field that points, I'm going to just draw the electric field in red here. So let's say the electric field, nice and uniform, points straight towards the top of the screen, or the top of our high point of the screen. So the electric field there, and the magnitude of the electric field as it points up is, let's see, what did it say again? I'll write it down, 6.2 times 10 to the 5th. 6.2 times 10 to the 5th newtons per coulomb, and it's pointing up in this case. All right, so now it's saying there's a surface, there's a flat surface, it has an area of 3.2 square meters. What is the electric flux to the surface when the electric field is perpendicular to the surface? Okay, so let's say here's our surface. I'm trying to draw it sort of three-dimensionally, but let's imagine that we've got this surface here, this flat surface like that, where the electric field is exactly perpendicular to the surface. So it's like the surface is horizontal as we're showing it here, and then the electric field is vertical. So that's exactly perpendicular to the surface. All right, so the electric flux through any surface, so we use capital A for that. And since this is a flat surface and the electric field is uniform, we don't have to do an integral. We could just say it's equal to E, the electric field vector, dotted into the area vector. If this was a surface that curved or the electric field wasn't uniform or something like that, we'd have to do the integral of E dot dA and then integrate over all the area. But here, since the surface is flat and the electric field is uniform, we can just say we're going to multiply times the area vector. Now remember, the area vector is always points, so the area vector points always perpendicular to the surface of the area itself. So notice in this case, the electric flux would be, as always, E, magnitude of E times the magnitude of A times the cosine of the angle between the area vector and the electric field vector. That's what theta is. Now here's the deal about this. Okay, yes, I know it says perpendicular. It says the electric field is perpendicular to the surface. But remember that the area vector is perpendicular to the surface as well. So the area vector points perpendicular to the surface in the same way that the electric field does in this particular case. So the cosine of the angle we're talking about here is the cosine of 0. So it's just going to be E times A. So it's going to be the electric field, 6.2 times 10 to the 5th newtons per coulomb, times the area, which they gave in the problem, is 3.2 square meters. Which, when we multiply them, 6.2 times 10 to the 5th times 3.2 square meters, I get 1.98. I guess I should probably use significant digits more often here, or proper significant digits more often. But I'll do it here. Here we go. So it ends up being 1.984, which if we take two significant digits here, which is appropriate to the, they're using 3 now. All right, I'll just use 3. 1.98 That's actually a 6.20 there is what they said. All right, times 10 to the 6th Newton meters squared per coulomb, and that's the unit of flux. Okay, so that's part A, when the electric field vectors and the area are exactly parallel, the electric field being perpendicular to the surface. Part B, it asks, what about determining the electric flux when the electric field is parallel to the surface? In that case, I'll do a little erase here maybe. Okay, in that case I've got the wrong vector here, or the wrong surface written down. I'm going to get rid of this arrow here as well. And I'll fix it in a minute. Okay. I'll fix my little red vectors. So there's still my electric field vectors. Let's say they're still pointing in the way we described. They're pointing straight towards the top. But now the electric field, or sorry, the surface that we're talking about is oriented vertically as well. Now the electric field the area vector points directly to the right for the second one. And notice that now when I perform E times A times the cosine of theta, the theta we're talking about here is a 90-degree angle between the electric field vectors and the area vector. The cosine of 90 is 0, so the flux for part B, I should put just part B here. So for part B, the flux would be 0, since theta equals 90 in this case. Or another way to put it is the electric field vector and the area vector are perpendicular to one another. And I think that answers all of Christina's questions from the discussion boards for the live stream. Are there any questions on that one from the group, from the chat? And I am going to erase that. Okay. So then Chase's question asks about what happens when we have charges placed inside of conductive solids or conductive shells or something like that. Sounds like kind of like what we did as an example problem, but let's look at a one that we can sort of get our heads around on that. So let's say that let's place a positive point charge, which has a charge of positive Q, and let's place it in the center. Oh, look at this, I have shapes. I didn't know I had shapes. Look at this. Anything can happen now. Let's see if we can do this. No, that doesn't work. It might work. Ooh, look, I can make circles. I can make way better circles than I can make even in class. This is amazing. Okay. So let's say that I place that, I have this shell of charge that has a radius of, that's right, I'm developing my paint skills as we go right there. Okay, so the radius of this electrically conducting sphere is R. And I place a charge Q, a point charge on the interior of this solid, or not solid, well, it's a conducting, electrically conducting surface that has an inner and outer radius. So there's a radius there to the edge, which I'll call R1, and then there's a radius to the outer edge, which goes all the way to the outside now, instead of just the inside, that's R2. So it's a really thin. Maybe I could. I don't know. Maybe I could do this even better. Let's see here. See if I can do it. I'm contemplating something awesome, of course. Because what else would I contemplate? I'm gonna make a bigger sphere. Even bigger. There we go. Alright, we're gonna move it. Look at that. Ooh, there we go. So what we have now is a shell of charge that it's concentric on Q. So this is like the inner radius, and then there's the outer radius of this metal sphere. Okay, so the inner radius is R1. The outer radius out to the edge is R2. And the question is, what would, let's, maybe we could ask what our electric field looks like everywhere. And I think we maybe did an example problem sort of like this before. Maybe in class, I don't remember, to be honest, but we could do something like this right now, no problem. We could just say, all right, well, let's look at the situation where, let's calculate the electric field at all distances from the origin where our little positive point charge is sitting. What's the electric field look like? Okay, well, I would say let's use Gauss's law on this one. It seems like a good way to go about it, to calculate the electric flux and then use that because of the symmetry of the charge distribution that we have here. Now, another thing to notice, because this was a multiple choice style problem that we did do. So let's say that this shell, the solid conducting shell, is electrically neutral like before. That's where it started. And we got this positive charge in here. Now, the charges inside of that electrical conductor are free to move. The negative charges that are in there would want to be as close to this positive charge as they can get, but they can't leave the surface of the conductor. So they would actually build up on the inner surface here. So you got negative Q would be distributed over this inner surface. And all the positive charges in this electrical conductor would want to be as far away from this positive charge as they can get. Coulomb's law causing them to be repelled. So they would go and get pushed to the outer surface, but they can't leave the surface either. They're stuck. There's no conducting path for them to leave it. So you have positive Q building up on the outer surface. Okay, and it would be distributed uniformly over this outer surface of the conductor. Now let's look at what that would mean for the electric field everywhere. So this is what I'm going to do. I'm going to say, let's start with, I wonder if I can, when I make a sphere here, I wonder if I can do something clever like, I don't know, the outline I could make like, no, that won't work. I can't do it. I wanted to make it a dashed line, but okay, I'm going to make it a different color. I'm going to make it orange for, all right, so this is going to be our Gaussian surface. So we're choosing a Gaussian surface to sphere because this whole charge distribution, whatever it is, has spherical symmetry. So if I move that here and I say, all right, well, let's evaluate the the electric flux on this orange surface now. Okay, well, I think you can see, because of the symmetry we have here, that the electric flux through the, oops, no, I don't have my brush back yet. Let's get that. All right. The electric flux through this, oh, I lost it. Well, what can you do? All right. Well, the electric flux through the surface that previously was orange is E dotted into dA for that surface. Okay. Now notice that the electric field here, due to whatever distribution of charge that we see here, whatever electric field we have here, it's always going to be pointing exactly perpendicular to A, or to the surface of A. So E dot dA becomes E times dA. We don't have to take into account the cosine. The electric field is also, because it's the same distance from all of the charges that would have been distributed in here, that electric field can come out. Because it is the same value at every point along the surface that we've chosen. Now, remember Gauss's law says that this electric flux is always equal to however much charge is enclosed by a surface divided by epsilon naught. Okay, so now the left-hand side becomes E times the integral of dA, which that's easy to do. The integral of dA is just the area. If the radius of our Gaussian surface there is little r, then E times 4 pi r squared is equal to the area. Okay, so equal to the electric flux. The charge enclosed is, well, how much charges are on the inside of this? Well, this is all empty space in here. The only charge is plus Q. We haven't enclosed this charge with our little sphere, so we just get positive Q over epsilon naught, and we see that the electric field is 1 over 4 pi epsilon naught, if I combine this in this particular way, 1 over 4 pi epsilon naught, which is the same thing as K, times Q, over, and we still got the r squared. It looks like the electric field due to a point charge in the side there. Okay, selection tool. Okay, does that make sense? Now, what if I were to make this this surface here that I chose for my Gaussian surface, what if I made it big enough so that it was bigger than R1 but less than R2? In other words, what if my Gaussian surface was in here? Okay, then I would perform the same thing except the R would be different. But the other thing that would be different would be the charge enclosed. It wouldn't just be this, it would be whatever charge there was on the interior surface here. We're not enclosing the charge on the outer surface, only on the inner surface. So, I know that the electric field inside of an electrical conductor has to be 0. So that means that this E has to be 0, which means at every point along that surface area. So when I'm performing this integral, if E is 0 at every one of those points, then this flux has to be 0, which means the total charge enclosed has to be 0, which means that this positive charge here and whatever negative charge is distributed on the inner surface of the conductor has to add up to 0. In other words, the charge on the inner surface has to be exactly equal to minus capital Q. Okay, hopefully that's clear. The other thing that happens here is imagine that you would make your Gaussian surface, which you can evaluate it, even bigger than R1, so it's the whole thing. Now it's a sphere that's outside of the entire distribution. Well, we would do the exact same problem here, except how much total charge is there on the conductor? Forget this charge in the middle for a second, but how much charge is there in this whole conductor? I said it was electrically neutral, so that must mean the total charge on the inner surface plus the total charge on the outer surface have to add to 0. So when I'm evaluating this, the amount of charge enclosed, there's no charge in the conductor overall, but there is still the charge in the middle, which is being enclosed. So for R greater than R1, the electric field would again look exactly like this expression. So what we have here for our overall solution is that the electric field looks like this for R. Sorry, that's supposed to. It's not. I don't want it to be a selection tool. We want it to be a brush. Okay. For this solution right here is true when R is less than R2, and also for when R is greater than R1. Or no, sorry, I got those wrong. When R is less than R1, and greater than R2, which is the outer size. So this expression for the electric field is true inside the conductor and outside of the conductor. And for R is between R1 and R2, so when R is greater than R1, but less than R2, that is the region where the electric field is 0, which is inside the conducting material itself. So these two, this solution here works for both of these. This solution here, E equals 0, is in the region between the inner and the outer surface of the conductor. Hopefully that helps Chase. Hopefully that's sort of what he wanted to look at. Are there any other questions that I can answer today before we call it? We're already at over an hour and a half, but I am perfectly willing to keep answering questions until you run out of questions. Are we okay? Hopefully I've paused long enough for folks a chance to ask. All right. Well, if there are no further questions, then I guess we'll call it a day. Thanks for your attention. The exam will be coming up tomorrow. I'll open it up tomorrow. Use the discussion boards if you're going through this stuff and you find you're not understanding something as well as you thought you did or something like that. Please feel free to just post that question in the discussion board and I'll answer it for everybody. I think that's probably the best way to do it because then other folks can get their questions answered as well. So I guess we will see you next week, but after our sort of on the flip side of the exam. Good luck on your exam and stuff like that, and I hope this was useful. We'll talk to you later. Goodbye for now.